Hi, I will show you how to use QuPath to perform a subtype analysis on enteric neurons. So first thing you do is to download and install QuPath and start the QuPath instance. I highly recommend creating a project. So go to project, create project, and I will create it in this folder I have here. I'll just name it QuPath project and select that folder. I'll create a project directory. And now you can drag and drop your image of interest. So I will use the sample. I'll use the image from the sample images folder within GAT, and it'll ask you whether you want to decide. You let QuPath decide what image it is, and we'll set image type to fluorescence. Just click import, and now you can see the images here. Just double click and load it up. So this is a data set from Spark repository, and look, it isn't a big tile scan, but this sort of analysis is aimed towards these large tile scan images, and QuPath is great software for these large images. But for now, I'll use this field of view to demonstrate the analysis. So with QuPath, you can it has great annotation and interface, and for a lot of object classification and pixel in options as well. So if you want to look at the different channels, you go to View, brightness or contrast. You can see all the 4 different channels here. So I think we've got, so I'll untick all of them. I'll just show, so this first one is chat. Second one seems to be NOS. Third one I think is VIP. And fourth one appears to be hue, or a pan-neuronal marker. So a general a recommendation is that you can see that the channel names here are not, they don't say what the name of the channel is, so I'll rename the channels. It just makes analysis easier. So apply, I think this was VIP. All right. So now we've got these 4 channels. It's just easy to identify them now. So a general workflow within QuPath is to, so generally what you do is if you have DAPI, for instance, you'd use DAPI to detect all the cells and then classify the cells based on expression markers. You'll use a similar sort of approach here where in our case we have hue as a pan-neuronal marker. So what we'll do is we'll detect all the cells based on hue, and then once we've done that, then we'll classify them into different subtypes. So within the GAT repository, the GitHub repository, you go to QuPath workflow, you'll see the neuronal model, which is this model file with the .pb at the end, and you'll see a few scripts. So with the .groovy at the end. So just download those and just drag those onto the QuPath, and you'll get this. Just move this out of the field of view. And look, all you need to do in this case is just click run. But before we do that, what we're going to do is we're going to perform detection of the cells on this whole image. But because it may take a lot more time to detect the whole image, we'll just select a small field of view. So if you go to annotations, so within QuPath annotations, you can select regions using annotations. So you go here, and I'll just left click mouse and just draw a small region and say, hey, I want to just test my detection parameters on this area. So click run, and this is a GAT, this is a cell detection window for GAT. So now it's saying choose the StarDist model. So this is the model which is part of GAT. So it's this model here. Probability and rescale factor, these are things which you may test a few parameters before you finalize on which works for you. I've gone into detail on rescale factor in the GitHub repository, but generally I'd recommend trying a factor of 1. And which channel do you want to use for segmentation? So because we renamed, it's easy to identify them. So I'll choose hue. I'll keep these default for now. This is a filtering the cells if they're below 90 micrometer per square area, delete them. If they're above 1000 micrometer square, delete them. So you can get rid of smaller and bigger objects. And then this is the name you want to give the objects that are being detected. So once you have this, just hit run, and it should, yeah, now it just comes up with this window saying detection complete. Now if you go there, you can see that this is what it's detected. Now it's a bit hard to see this, so what I'll do is I'll just move these windows out of the view, and we can change this to grayscale, so it's easier to see. Now, because the yellow outline is quite thick, we can actually control the opacity of the outlines using this here, this slider here. If you want to fill the cells, you can fill the cells with this color, or we can just show the outlines. So these are what you call detections. So I think it's done an okay sort of job, but it's missing a few cells. So we can play around with the rescale factor as a start. Let's try this, 0.9. Yeah, so I think it's detected this one here. Not too bad. Again, if it's not picking up cells, it's probably because you may have to reduce the probability score. So I would give 6.5 for instance. But this means it may pick up more background as well. So you can see that it's picked up a few cells there. So the rescale factor, so it depends on how you go about selecting it, but I may just show you quickly what the rescale factor means. So if you go to the wiki page, I've gone to details on choosing the right parameters and what it means. So if you choose a larger rescale factor, means that the objects will be split. If you choose a smaller rescale factor, the objects will be merged. So just keep this in mind when selecting the rescale factors. So I'm going to go with this setting over here. So once I'm happy, I will now want to select the whole image. So you don't need to close this window. It's fine. So we can delete this one here, this annotation here, because we don't need it anymore. We don't want to keep anything that's been detected. And we go to objects, annotation, and let's create a full image annotation, which means select the whole image. Now annotation comes up here, and this is the whole annotation. And now when we run this, it'll run on the whole thing. So say if we didn't have any annotations here, I'll just delete it, and you click run, it'll say, oh, it should have given a warning actually. Yeah, well, just run it again, maybe. Yeah, so you can see that it says please select a parent object because the window is already open. So if you're running this and there's no selection here, it'll say please select a parent object. So objects, annotation, create full image annotation. Now I click run, I get this. Now here I choose the StarDist model again. So the model. Just keep in mind these models are different from the ones from Fiji. The Fiji models, the ones in Fiji have been converted to work within StarDist. And I think it'll 0.65, 0.9 I think. I want to detect on hue, keep everything the same, and then whatever is being detected, I want to name them hue. Because whatever is being detected, it comes a detection, but it may not have a name. So we need to say, okay, whatever's detected, I want to give it a, you can give it whatever name you want. Like run, and depending on how big the image is, it may take a while. Yeah, it's done. So I'll just close this and just keep this to the side. So yeah, I think it's done a decent job of detecting cells. It's got most of them. So the main thing is you need to verify this. So if you have a really big image, draw a few annotations, a few different places, and run it and make sure it actually detects what it's supposed to. So now we've gotten here, and say now we want to get the number of chat cells. So within QuPath, what you can do is you can use because we've already gotten a detection, we can do what you call an object classification, where we are saying, okay, out of all these things that are detected, now I want to classify them into different classes. So I want to now classify them into, let's just do chat and NOS in this case. So let's try with chat. So with chat, you can see that it's quite bright, and it doesn't seem as difficult compared to NOS, for example, where you see a lot of these fibers going through each cell. So we can use just the intensity of the cell to classify the detection. So what you can do is go to classify, object classification, and say create single measurement classifier. What that means is all the detections, get all the detections, so use all the detections, use only chat, and look at the mean intensity of each detection, and if it's and then set a threshold, and if it's above the threshold, then we can say it's chat, and if it's below, we just leave it as is. So what you can see is that we don't have any classes here. So whatever classes we want, we define them. We enter the details of the classes in this box here. So what I'm going to do is I'm going to say, hey, I want to add a class for chat cells. And yep, and now if I look here about threshold, I want to classify it as chat. It comes up here. And one great thing about QuPath is there is a live preview, so you can adjust the threshold and you can sort of figure out what is the best value. Now here you can see that it's got a bimodal sort of distribution, so I would say something in the middle of these two is probably the best way to go, because this is probably more background and this is probably a bit more of the signal. But look, the visual way is obviously the way to be really sure. In ImageJ you can use automated thresholds, but whatever values you use here, make sure you use it consistently throughout your project, and that's how you can that's how you eliminate subjectivity. So doesn't look too bad. So let's say we settle with something like this. We're saying chat above threshold is chat, below threshold I haven't defined anything, and then I'm just saying now we can create a classifier. So what this is you're creating this sort of I guess a classifier here, or creating a method here saying, okay, if these detections are above a threshold of 108, if the mean intensity of chat within these detections above 108, they're considered to be chat cells. So now you click apply, sorry, you click not apply, you click save, and that's saved as a chat classifier. So don't click apply yet. What we're doing is we're building, well, once we've done this, now I'm going to create a classifier for NOS. So I'll show you why we are not applying it yet. After I create a classifier for NOS. So NOS may be a bit harder to create a similar classifier just because that it's more noisier, there's a lot of fibers running through. Say for example, if I'm going to use mean intensity, if you click on each cell you can view the measurements. Here it says the NOS mean intensity is 168 for that cell, and I can go to say maybe where there's a fiber running through it and I'll get a similar sort of value. Or so for example, if I click here, the mean is, you still get 73, but there's like a fiber running through it. This here, the NOS mean is 80. So it's a bit more noisier. So what I would say, we can use a different method to look at this, to create a classifier. So for this, you do object classifier. Another way is to train an object classifier, where here what we're going to do is we're going to annotate an area saying this is NOS and this is not NOS. So before we do that, we need to create a class for NOS. So I'm saying add NOS, and now I'm going to say classify, object classification, train object classifier, and you're going to look at all detections. That is, you're going to go for all the detections, like all these cells you detected. This usually gives a really good performance, the artificial neural networks, so I would go with this as a start. The random trees also works well, but I usually default with this. Feature, I'll just go with all feature measurements. Classes, okay, so here I'm going to say I want to, oops, alright, that's good you saw that. So what happened is now, once I create a NOS, now I want to annotate it. When I say annotations, what I mean is we go in and we select areas and say this is what NOS is supposed to be. So now I'm going to go with this brush tool here. So with QuPath, if you zoom in, the brush tool is small. If you zoom out, the brush tool is big, which is great because you can annotate areas accordingly. So now I'm doing Control Z to undo. Alright, so I'm going to go in here and I'm going to, oops, I'll label this and I'm going to say that this is NOS. So I select no. Once I know this what I want, I select that and I click set class. So this annotation is NOS. I can say this annotation here, it's changed into the color for NOS, and this region here I've said it's a NOS cell. Now I'm going to go around and I'm going to label a few NOS cells. Set class. I'm going to go to lighter NOS cells just so I can tell the program the light stuff here is also NOS. Cells, yeah, cells there. So that's NOS too. NOS as well. Alright, so got a few. I'll do this as well. Got a few here. Now let's see how all this works. I will increase the opacity and maybe I'll change the color to something like red. So if it's NOS, it'll become red in color. Alright, so those are the annotations we had. Now we're going to say, okay, I only want to do NOS, click apply, and I want to use the unlocked annotation. So when I say unlock, the whole image we selected is a rectangle. If you right click, it'll say lock, which means it's locked, you can't edit it. So it's good to leave it locked because that way we want to use that for training. We'll only use all these things we've annotated separately for training this classifier. So select a NOS, click apply, unlock annotations. Now I can do a live update to see how well it worked. Okay. So this is another thing. So what happens is you can't train a classifier with just one. Um, you need to say, okay, this is NOS and this is what NOS is not supposed to be. So now I can go here and I can say, okay, we can use the ignore class. We can go and say, hey, these stuff here, just set as ignore class. Like they're not anything of interest. I'll do a few more of that. I think where there's some really nice fibers running through cells, yeah, this will be a good one. Okay, so now I've created a few annotations. Just make sure you have somewhat equivalent annotations for both different classes. Go to select, I click ignore, apply. Now I click live update. When I click live update, you can see that with all the annotations, it seems to have the color for the other one is probably red as well. That's why it's giving. Similar color. Let's change the color to something else, just to avoid confusion. Yeah, okay. So it's just the color of the ROIs we had. So you can see that the magenta ones are changing color to magenta. So the NOS are now all magenta in color, and these cells, the other cells, they are all the non-NOS cells are all red in color. So this looks pretty good. I think a few annotations we got some nice output. Oh well, actually, yeah, this is probably one where it doesn't look good. So I'll just go this. So see, it's already updated automatically. So this is why the feedback is really good. I really love QuPath give very live feedback, and it's very interactive, intuitive to use. So once you've done this, well, there's another one where it's positive actually. Oops. It's positive. So you want to do multiple at the same time, press Control. Oh, sorry. Oops. It's not Control. Where's that annotation? Yeah. Actually, I can select both here, and I can just set that as NOS. But then, yeah, so the other side is like that when you do that, then other things may get updated. So that's why providing more annotations may make it make your training more accurate. All right. So say you're happy with the training, you're good with this, then you go, okay, create this classifier, save it as nnos, click save. Now I've created an nnos classifier. Now we haven't really, like, I mean, in this case it applied it, but technically we didn't apply the chat classifier yet. So now what we're going to do is we're going to, since we have, say, two classifiers here, now we're going to apply them simultaneously to our image. So we go to classify, object classification, create composite classifier, and say, okay, put all our chat and NOS classifier together. And we say, okay, this is called chat NOS, and we save and apply. And now we just save and apply it, and now we've got a classification where it said, okay, these are NOS, these are chat, and both, and they're positive for both as well. So we get that information as well. So once you've done this, I guess, how do you extract the information, right? So to do that, you go to measure, and because these are detection measurements, if you want data for each individual cell, you get show detection measurements, and you get data for every cell. Like, and it's interactive as well. So you can click here, and it'll go to that cell. So it'll go there, and it'll see, and you can see what cell it is. And you can get all the information such as the area, circularity, diameter, the intensity in chat channel, NOS channel, hue channel. You get all that information. But if you just want the counts, you can just go to annotation measurements. So you can get the summary of the measurements for this particular annotation. So if you click that, you can just look here. You can say, okay, number of detections. There's a number of cells, 1030. Number of chat is 517. Number of NOS is 310. The cells that are both are around 11. So if you want that in the table, you go to measure, show annotation measurements, and this is an annotation, so you just go and get that from there, and you can get on the table. You can do similar things for the VIP channel as well, and then you can you can create quite a few, and then you can classifiers and create a composite classifier based on all these, and you can populate it, and then you can apply it. And this is how you can get all the subtype specific information. So thank you.